Our chief guest today, Professor Arul Lakshminarayan sir, respected professors of Cochin University Physics Department and APT members, dear students. We have gathered here today for a very proud event, annual event of Academy of Physics Teachers Kerala, Professor Valsakumar Memorial Lecture. It's an annual event we have been conducting since 2019. This is the seventh memorial lecture. So before going to the welcoming address, I would like to introduce Professor Valsakumar sir to the new audience, to the students. Professor Valsakumar was an honorary member of Academy of Physics Teachers Kerala. He was a renowned physicist and a teacher from Kerala. He was a scientist at IGCAR Kalpakkam till he superannuated as outstanding scientist and head of materials physics division in 2012. Since then, he had been a distinguished professor at Hyderabad Central University. And when IIT Palakkad was instituted, he was there for 2-3 years. He was a versatile researcher. Some of his seminal works on open quantum systems and statistical mechanics became landmarks in those subjects. His research interests spanned from quantum field theory to computational material science. He is also remembered as an inspiring teacher, fondly called Valsasar by students, with a deep understanding of different branches of physics and mathematics. His untimely demise at 2019 was a great loss for Indian physics community. So since 2019, his family and friends, colleagues instituted this annual memorial lecture. So eminent personalities in the previous years, eminent personalities like Professor Ananda Krishnan sir from IAC, Professor Sahu from IGCAR, formerly at IGCAR, and recently Professor G. Bhaskaran sir from IMSC, Sri Ram Kumar sir from IIT, and last year we have Govind Krishna Swami sir from CMI. So this year, this seventh memorial lecture will be delivered by Professor Arul Lakshminarayan sir from IIT Madras. And he will be presenting a talk on quantum entanglement. Entanglement, a sojourn to the heart of quantum. That's the title. So this year, as you know, this year being the International Year of Quantum Mechanics and Quantum Technologies, we think that this particular topic on quantum entanglement, which is at the core of quantum mechanics, this will be very useful and interesting to the physics community. Professor Lakshminarayan sir, Arul Lakshminarayan sir is a leading researcher in quantum information in India. Recently, he had some recent papers are in Physical Review Letters and Physical Review Series, and different recent papers are there. So I would like to, with all, when we approached him for this talk, this year's talk, he was very glad to accept our invitation. And I think he's also aware of Valsakumar sir's work through his friends and students. So with your permission, on behalf of Academy of Physics Teachers, I warmly welcome Professor Arul Lakshminarayan sir to this event. Welcome, sir. I welcome all the physics community of Cochin University Department. This is in fact a collaborative program of Cochin University Physics Department and Academy of Physics Teachers. Since 2022, this annual lecture series is being conducted in CUSAT Physics Department. So some of you may have attended the previous lecture also, last year's lecture also. So in fact, many of the teachers of physics department here have been office bearers of Academy of Physics Teachers. Our Jairaj sir was a president of Academy of Physics Teachers for 4 years, I think. So all the physics professors or the faculty members of Cochin University Physics Department, welcome all of you to this program. And Valsakumar sir's family is here. His wife Leela madam is here. Her cousins are here. So and APT members and Secretary Santosh Potre sir, other APT office bearers and members are here. I welcome all of them to this program and all the students here of Cochin University's department, all the students. On behalf of Academy of Physics Teachers, I welcome to this program. Before the commencement of the talk, I invite Dr. Santosh Pothare sir, Secretary of Academy of Physics Teachers, to share a few words.
A very good afternoon to all of you. The resource person for the day, Professor Arul Lakshminarayan, dignitaries on and dignitaries in the dais and the on and off the dais, office bearers and members of academy, colleagues, dear students, and beloved members of Valsakumar. As far as Academy of Physics Teachers is concerned, the Academy is reaching out to the Physics Academia of the state through various programs. We used to conduct workshop series for students as well as teachers. Some of the programs are already completed and many are going on. A project symposia is going on. The first part of physics talent search examination have concluded. Then we have the academy's bulletin is being prepared. And there are programs yet to come which will enhance the teaching and learning process in the state, science in general and physics in particular. I'm really thankful to all the members of the academy for their support. And today, we are proud to arrange this 7th Valsakumar Memorial Lecture. I remember attending Valsakum's lecture organized by APT. I think he was the resource person in many conferences and workshops. I could see the way in which he presents his lectures. As far as a teacher is concerned, how he presents his blackboard, how much orientation he had with while he was lecturing. So there is an entanglement to that blackboard. And I take this opportunity to express my sincere feeling of gratitude to the members of Valsakum's family, his colleagues, his students, and well-wishers for instituting such an inspiring initiative. Today, the resource person for the day is Professor Arul sir, and he is presenting a lecture on a very relevant topic. It is relevant in many ways. It's connected with the Physics Nobel 25. It's connected with the centenary of quantum science and technology, which is being celebrated all over the globe. And also, as the basic science which paved way to the important fields of electronics and computer science, which is making our life in the way it is now. I congratulate the coordinator coordinators, Dr. Hari Krishnan and Dr. Sasidevan and their team for elegantly coordinating this. I request all to support the activities of the Academy to enhance the process of teaching and learning physics in the state. Once again, I welcome all of you to this gathering and handing over the session to the resource person for the day. Thank you.
Good afternoon, everyone. A short introduction of Professor Arul Lakshminarayan. It's a real honor to introduce our guest speaker today, Professor Arul Lakshminarayan, a distinguished physicist and professor at the Indian Institute of Technology, Madras. Professor Lakshminarayan completed his B.Tech in Mechanical Engineering from IIT Madras and went to earn his PhD in physics from State University of New York at Stony Brook. He is a recipient of INSA Young Scientist Award for theoretical physics and has worked at world-renowned institutes including Max Planck Institute in Germany. He is a fellow of INSA as well as Indian Academy of Sciences. His research interests include quantum information, quantum chaos, and complex systems, areas that are shaping the future of physics and technology alike. At IIT Madras, he is not only a leading researcher, but also a passionate teacher. We are truly delighted to have him with us today to share his insights and experiences. Please join me in welcoming Professor Arul Lakshminarayan.
Hello, everyone. Can you hear me? Is that good? How is this? I think I've put it on. Okay. Okay. Good. Yeah. I think that's fine. So good afternoon, everyone, and it's a real pleasure to be here. I'm very happy to be here, and let me start by thanking Dr. Hari Krishnan, who invited me here, Srimati Leela Valsakumar, and colleagues for supporting this venture, supporting this series, initiating it in the first place, and the Academy members, and for a very generous introduction, Asha. It is, I think, from my point of view, from Chennai, well, from what I'm seeing, I think Kerala has a very unique environment of physics education, and academy and other colleges, all part of this. I think we can see the effects of it in the demography of physics researchers in India. And many of you, I have had many students from this part, and it's lovely to be here and share with you some little insights which hopefully excite some of you. And yes, so I'm especially happy to be here for as part of this series where my teachers like Professor Balakrishnan have also spoken in the past. I have had not great interactions with Professor Valsakumar in terms of the intensity of interactions, but I said certainly he was one of those people you would hear about in hushed tones or in awed tones in the Madras, Chennai physics community, and I know many of his students and colleagues. Uh, and also later on, when he was in IIT Palghat, what a fantastic person he was. So it's all the more a pleasure to be here and talk about some of my interest in physics. And I chose entanglement because Dr. Harikrishnan said it's also the 100 years of quantum. So please feel free to stop me at any point if I'm not clear or you would like some clarification. But maybe first I should start with some clarification as to, it's now 2:23, about an hour. Is that so? Yeah. So yeah, I'm sorry, but the first slide seems to be very blurred. This is from a Scientific American article, which was actually around 2001, because there's many hundred years of quantum mechanics. Quantum mechanics itself, we had Planck around 1900, so this was that 100 years, and there are so many landmarks of quantum physics from Planck onwards, but you can see this a series of peaks here, which is where Schrödinger, Heisenberg, all of that, the frenetic activity happened. And in fact, the first peak here is Bose-Einstein condensation. You don't see that very well, but in fact, that happened even before Schrödinger equation with the revolutionary work of S.N. Bose, uh, who invented the entire statistics which clarified photons and the entire black body radiation, which from the time of Planck was around, but was rationalized into the important identification of symmetry and identical particles happen there. And then with all this flurry of activity, there was an intense amount of activity when in the 1930s, people were consolidating and sort of thinking back and saying, what does all of this mean to some extent? And everyone who did that, from Niels Bohr to Einstein to Schrödinger, were all pioneers in this field. And Schrödinger, in his famous, what is even today called Schrödinger's cat, he formulated the essential heart of quantum mechanics, not as superposition, but as entanglement. And I will tell, I'll shortly, we'll see what he said exactly. And I think the German word is Verschrankung, so as entanglement. And once he formulated that, didn't take very long for Einstein, Podolsky, and Rosen in their famous 1935 paper to use that and to say that, look, with additional very reasonable assumptions, which they called locality and realism, we'll talk about that a bit, this led to issues. And they said, therefore, quantum mechanics was not complete. And this led to, as people know, a very prolonged debate between Niels Bohr principally and Einstein. And so all of that happened in the 1930s, and entanglement was the central player there. And as far as this story is concerned, entanglement, there are so many other things which I myself can't read from this range, but there were tremendous experiments and beautiful concepts were being developed along the way. In the 1950s, Bohm formulated the ideas of EPR in a more precise manner and a simpler manner, in which it was thought about later, using just spin half and two-level systems rather than position and momentum. And then in the 60s, there was this path-breaking work of John Bell, who took it to something which is testable in an experiment. All the arguments, the philosophy of Einstein-Bohr debate. and whether there is realism, locality, quantum mechanics, whether that is something which is fundamentally different. And then a whole series of developments happened till experimental work, which I will detail a little bit, happened also, importantly. Uh, and we will see what the experiments, the judgment of the experiment, after all, that's the final arbiter, is nature herself, had to say about these issues. And then in the 1990s, people started realizing that entanglement was not just a kind of cute thing about physics or quantum mechanics, which led to very non-classical effects, but maybe can be useful for various um, tasks such as cryptography. In fact, the earliest developments was towards cryptography, secure cryptography. In fact, probably the earliest thing was money, so quantum money, uh, which which was probably not published in that sense, but cryptography became the central application of some of these ideas, including entanglement, not just entanglement. And then with the development in the 1990s of quantum computing, entanglement remained an important aspect of that, but it was taken up by the development of quantum computers. We'll see that a little bit. So, and then I will talk about why entanglement, although it was recognized and formulated by Schrödinger in 1935, is even today only poorly understood, and why there is so much amount of scientific work on understanding this and its applications, and that it's far from over. And all the young people in this audience, there are so many questions, absorbing questions to address, as well as the senior members. So, yeah, so Schrödinger himself, in his words, talks about entanglement in the following way. When two systems enter into temporary physical interaction, they can no longer be described in the same way as before. I would not call that one, but rather the characteristic trait of quantum mechanics. By the interaction of the two representative, the quantum states have become entangled. So basically, he's saying that when two particles are interacting, the states which are as a result of this interaction are very different from the states without the interaction. So in a very pictorial manner, let us look at two coins and write the state of these two coins. Both of them can be head, one of them head, other tail, tail, head, tail, tail. There are only four possibilities. And when we enumerate these kind of possibilities, it's essentially a classical object. And these are all classical states of these two coins. You can think about entanglement as a real state in which there is a possibility of both of them being head as well as both of them being tail, in a way at the same time, so to speak. So there is a state which is a superposition of both of them being head and both of them being tail. Now, if we were to present one of these classical states to anybody, to ourselves, and to ask what is the state of the first coin, it won't be very hard. So let me take this particular third state here and ask you, what is the state of the first coin? Can you please tell me? Huh? Tail, right? And the second? Head. And so that's all. That's how it's kind of, I have assumed that the second bracket I'm writing here is the second coin. But now if we ask ourselves the same question for this state here, it seems like we cannot really answer that question, whether it is head or tail. Okay. in fact, it is not possible for us to identify the state of a single coin. By the way, it's not just because I've put a plus sign there. For example, if I don't have that on my slides, I think. If we had a plus sign of all of them, HH plus HT plus TH plus TT, and then I was to ask you the question, what is the state of the first coin? What would your answer be? I've now taken a superposition of all possible classical states, right? And let us now ask the question, what is the state of the first coin? It's not obvious because it's a superposition of all of them. However, when you're taking an equal superposition of all of them, you can just think about it like some factorization. X plus y into x plus y. So this will be actually the first coin will be in a state head plus tail, which is fine. A single coin can exist in a superposition of head and tail. First of all, that's a superposition principle of quantum mechanics. In addition, there is this other property. So if all of them are equally superposed, the first coin can be head plus tail and the second can be head plus tail. And you can assign a state to each of these coins. However, if it was head, head plus tail, tail, if you write this as even a superposition state of head and tail in the first coin, and a superposition state of head and tail in the second coin, it is not possible for us to do this. In that case, you would call this state an entangled state. So the fact that you have superpositions and you have classical states like this, if we call these classical states, leads to entanglement in a very natural manner. And now what is so, this very simple state, the fact that we cannot tell what is the state of the first coin, but what we have done, we have specified the state of both the coins. So please just step back for a minute and let's think about this. How strange it is. We are specifying the state perfectly for two coins, but we cannot specify the state of a single coin. Classically, this seems like it's not possible. For example, let's take two objects like this phone and this glass here. There is position and momentum for each one of them. If we specify the joint position and momentum for both of these objects, from that you can infer what is the position momentum for the first object, position momentum of the second object. No problem, even if they are interacting. They can do whatever they want. It can be strongly interacting, still specifying the state of these two objects necessarily has in it information about the state of the single object, the constituent objects. But quantum mechanics allows for such states where both of them are in one possible definite state, but the individual states are not. So let us see this further. So just for, I will kind of intersperse some mathematics for those of you who are familiar with this, it's fine. Otherwise, you can just think about it a little bit more broadly and go ahead. So a state of a quantum system will be entangled if it cannot be written as a state of a first system times or a tensor product state of the second system. You cannot specify the individual states of the subsystems, but you can specify the entire state. Then you will call that state entangled. So there is a generalization to mixed states which is written like this, but let me just tell in words. An entangled state cannot be produced by local operations in classical communications. So that means that you cannot be one person in Cochin, another person in Chennai. There is a laboratory in Chennai, there's a laboratory in Cochin. We decide to communicate however we want and to apply local fields on two of the particles which are there with us. The state which we produce will never be entangled. They can be correlated. For example, we can take one spin and put it up, and the other will also be up. You say this spin is up, you also make it up. They'll be correlated, but they cannot be entangled. Entanglement always requires what Schrodinger realized very early, that they interact, enter into temporary physical interaction. Okay, so maybe I can skip this. This is like postulates of quantum mechanics. And can I skip this? And I'm assuming that all of you are physics students. So there is a state which is described by a state psi or a vector psi in a Hilbert space. I think that is sufficient level of detail. This is in fact from Wikipedia. Composite systems, more than one systems, described by this thing called a tensor product. It's basically like a product of vectors. Then there are these postulates about operators, observables as Hermitian operators, and what happens most importantly on measurement. This is all traditional quantum mechanics. And the fact that there is a measurement, the most important thing about a measurement is that it leads to a probabilistic outcome. So this is again a major departure from classical mechanics, and this is still a matter of investigation known as the Bond's rule, the origins of the Bond rule. That the probability of an outcome, which is an inner product of the state with the state of the observable. Okay, so let me go ahead, and in fact, this is again Schrodinger. The best possible knowledge of a whole does not necessarily include the best possible knowledge of all its parts, even though they may be entirely separate. Separate meaning that they are one in Chennai, one in Cochin. It is rather discomforting that the theory should allow a system to be steered or piloted into one or the other type of state at the experimenter's mercy, in spite of his having no access to it. So Schrodinger expresses some reservation and some discomfort at the thought that you can have these entangled states which are separated, well separated, but you can steer the state of a distant particle by some local means here. What is happening in Chennai, you can steer by what you're doing in Cochin. So let's see that in some more detail as we go by. So by the way, this words like steering and so on is much more modern. I mean, Schrodinger used both steering and entanglement, but both of them really flowered only in the 1990s, and later steering was understood and in much more detail. So let's look at this. I said that Bohm simplified the analysis in terms of spin particles. So spin half, let's say that there is a source which is emitting two spin half particles. So one is going to the right, and we'll call that Bob, and to the left, Alice. So this is standard information theory jargon of Alice and Bob. And so there are the state of these two spin half particles is given by this spin singlet. Actually, is this visible for those in the back? Yeah, okay, good. So there's a superposition of up, down, down, up. So the spin singlet state. And this is along a spin in the z direction. And the laws of quantum mechanics about measurement says that if you do a z measurement on this, the spin z component measurement, then there is a probabilistic outcome. As we said from Bond's rule, at probability half, you will get this plus minus, and with probability half, minus plus. So these are these two kind of head, tail, tail, head states. And there is this superposition, which is created by a natural decay process of some kind. And because of some symmetry or something like that, they are born entangled. And there is this, but once you are making a measurement, it breaks that entanglement. And you can then say for sure whether it is plus or minus. But you see, both these possibilities are allowed. And therefore, if Bob and Alice, Alice measures a plus, she knows for sure that Bob has a minus. And if Alice has a minus, she knows for sure that Bob has a plus. But she has not done anything in her lab other than measure the Z component. So you can't say that she is steering Bob or influencing Bob in any way. It's just that she knows what is the result of Bob's outcome by just knowing her outcome. Now let us see that this is where the thing gets more interesting, is when you make a measurement in some other basis. This is in the X basis. So you're measuring not the Z component now, but the X component. And the same singlet state can be written as a superposition in the same way, where Z is just replaced by X. So that means there is a superposition of, in the X measurement, also plus minus and minus X, like head, tail, and tail, head. And when you make an X measurement, then you will get plus minus in X or minus plus in X. Now you see, Alice can decide what measurement she wants to make. She can say, I'm going to make a Z measurement or an X measurement. She doesn't have to inform anybody, free will of Alice. So if she measures in the Z basis and gets a plus, then she knows that Bob's state is a Z minus, for sure. But she could have also chosen to measure X component of her spin particle, and if she gets a plus in X, she knows that Bob's state is minus in X. So she has in some sense steered the state of Bob into the X eigenstates, whereas if she had made some other measurement, she would have got a Z eigenstate. So this is the discomfort which Schrodinger was talking about. The discomfort in the theory should allow a system to be steered or piloted into one or the other types of state at the experimenter's mercy. So in fact, it's much worse. It's not just Z, X, or Y, any direction. So there are an uncountable infinity of directions that Alice can choose to measure, and she can, depending on the choice of her outcome, she knows that the other state is prepared exactly in that state. So this seems to violate a lot of things, what we think about as locality, especially, that there is no signal can travel faster than the speed of light, and therefore, this seems to have there is an issue with that, because instantly there is a state change in Bob's particle. The other is what Einstein, Podolsky, and Rosen call realism, which is that a state of a particle, when you make an observation of it, and you are seeing an outcome of that observation, it is simply revealing a pre-existing property. So let us say that you don't know what is there, in my hand, and I reveal it to you, and you see that, well, it's not a glass of water, but it is a cell phone. What I had in my hand before you made that observation was also a cell phone. It's just that your observation just gave you that information. It did not change some phone into a glass of water or vice versa. A phone was not created by your act of seeing it. That is realism. That if you measure a particle's, let's say that you don't know what is the speed of a particle, you measure it and you find it to be 5 meters per second. Even before you measure it, it was 5 meters per second. That is realism. It seems obvious to us because that is classical understanding and classical intuition. Now, both of these were called into question by these simple states which are there. So to see this more clearly, I kind of wrote a pictorially what happens. Let us imagine the following. Alice and Bob share two particles. I mean, there are two particles, one with Alice and one with Bob. And let us think about this head-tail kind of measurement of a coin. And let us say that Alice is measuring her particle, or she has many particles and she is measuring whether it's head or tail. And each time she measures it, she gets a different result. So there can be head, the next can be tail, and the next is head, and so on. Okay, it looks random to her. Each time she is measuring it, it looks like a random number, head or tail. But what is interesting is that if these two particles are entangled, like in that state which I wrote, head, head plus tail, tail, then each time she gets a tail, Bob will also get a tail. Each time she gets a head, Bob will also get a head. But each Alice and Bob will look at this sequence of head and tail as if it was completely random. So it's like, imagine that you're tossing two coins, two people are tossing two coins. They're looking just as random as a normal coin, except that when they measure, when they compare, they see to their great surprise that both of them have got the exact sequence of head and tail, which is a very unlikely event. Not zero probability, but you can work out that it's a very unlikely event, right? So, but that is exactly what Alice and Bob will get if these two particles were entangled. And I've put here space-like separation. People like to say that to ensure that there is no possibility of any communication. Space-like separation means that these two events of observation of Alice and Bob are two events which cannot be connected by any signal. So speed of light is the maximum speed at which signals can travel. So the measurements are made in such a way that no signal, if Bob is making a measurement at some time, Alice, no signal can travel. So let's take light. So the light takes a certain time to travel from Bob to Alice. Alice must have made that measurement in that interval of time for which Bob has sent the signal of light. That's space-like separation. So in a way, so this is sometimes called shared randomness. That's the jargon of modern quantum information, that they are sharing randomness. Each one is random, but somehow they are able to share it perfectly. They are correlated. So things get, by the way, this is not something which is classically not allowed. You can have two coins which are mysteriously somehow, twins, and they are completely the same. There is nothing which is, it may be an unlikely event, but not an impossible one. So this is how you may describe it. Probability that there are two heads is 1/2. Probability that two tails is 1/2. And this anti-correlation never happens, for example. Random locally are always identical. Now let us assume that there is some other measurement you can do, the same Alice and Bob, same particles, but you can do some other measurement, not head and tail. You can look at the color of the coin. Okay, and there are again only two possible colors, let's say red and blue. Okay, and they find that the same thing happens, that when they measure the color, there is a perfect correlation between these two, but in fact, they appear to be completely random. Each of them appears to be completely random. And to make the analogy with quantum mechanics, this color and the head-tail cannot be simultaneously specified. Okay, this is the non-commutation of the x and z components of spin in quantum mechanics. The fact that you cannot have, this is the uncertainty principle of Heisenberg, and you cannot make sharp measurement of conjugate variables. And therefore, in fact, this let us think about this head, tail, and color as these two kind of conjugate things, measurements or variables or observables. Then you cannot have them to be measured the same. You can't say that here is a coin with this head and the color is red. That is not possible in the quantum context. So now let us maybe make life a little bit more interesting and say that Alice can measure head or tail, and Bob measures color. So it's not as if both are measuring color or both are measuring head and tail. Let's say Alice is measuring head or tail and Bob is measuring color. Then there is no perfect correlation. All of the four possibilities are allowed. When you have a head, Bob can get blue. Tail, also Bob can get blue. So there are 4 possibilities and all the 4 are allowed. But actually there are correlations, there are subtle correlations across such incompatible measurements that depend on the quantum state and the measurement basis. So we are getting now closer to what is called Bell's inequalities. And so let us actually make it more, this is how Bell himself visualized this. It's not just one measurement done by Alice and one measurement done by Bob. To see the full power of this, you need to allow Alice and Bob to make 2 measurements. Okay? So Alice makes a measurement of 2 possible observables. Let's call that A1 and A2. And Bob can make 2 other possible on his particle, B1 and B2. And again, for simplicity, let's just keep it like 2 possible outcomes, like color, and color is red or blue, or so let's give values plus minus 1 to these things. So each of them measures 2 possible outcomes, each with 2 possible outcomes plus minus. So Alice has this kind of situation which I have marked here. The first coin has, so the first measurement, let's call this A1. The measurement possible outcomes are head and tail, head or tail. And if she chooses A2, it can be this blue or this red color. Okay? And depending on her mood, that particular moment, she can either choose A1 or A2. Nothing deterministic about that. And similarly, Bob can measure some other head and tail. I'm just writing that as H prime, T prime, and some other set of colors. Okay, 2 possible measurements, B1, B2, 2 possible outcomes. And then what they do is they construct this kind of a quantity. So they make a lot of, so there are, assume that each of these are entangled particles with Alice and Bob. They have, let's say, 1 million such entangled particles, all identical copies. And Alice has a series of measurements, A1, A2, A3, etc. A1, A2, A1, A2 in some sequence, and the outcomes are plus minus 1. So she has a ledger plus minus 1, outcomes A1, A2, and B, similarly, Bob has B1 plus minus 1, B1, B2, etc. And then they come together and they compare these 2 ledgers, and then they calculate, let's say that they find that in one particular pair, Alice has computed A1, has done the measurement of A1, and Bob has done measurement B1. Then what they do is they multiply, in that case, A1 and B1. Okay, whatever the value is, it can be 1 and 1, they will multiply 1 and 1 and get 1, or it can be both minus 1, or 1 can be 1, another can be minus 1. And similarly, if they find that in one particular instance, Alice has measured A1 and Bob has measured B2, they will multiply A1, B2. So there are only these 4 possibilities, A2, B1, A2, B2. Okay? And then they make this combination here, A1, B1 minus A1, B2 plus A2, B1 plus B1, A1, A2, B2. So there are 3 plus signs and 1 minus sign here. Okay, and then they have done this million calculations. They will take an average value of this quantity here. Now, what can it be? Let us think. Each of them can be only plus or minus 1. So let's say that Bob, B1 and B2 can be both 1 or minus 1. Both can be, if they are the same, they can be both 1 or minus 1, in which case this will become 0 because B1 equals B2. And this will become 2 or minus 2. And A1, A2 can be only plus or minus 2. So in that case, it will be plus or minus 2. If B1 and B2 have different signs, B1 is not equal to B2, then B1 plus B2 should be 0, and this will be plus or minus 2. So you see, a very simple argument shows us that this combination can only be plus or minus 2 at every possible A1, for every possible values of A1, B1, etc. And therefore, if you take the average over some million such particles, that is this average here, and take modulus, that will be less than or equal to 2. Because sometimes it can be 2, sometimes minus 2. So addition can be giving you 0. Okay, so but it cannot exceed 2. Do you agree with me? Are you the students? So it's just this plus or minus 1 makes life much more easier for us. And what is quite easy to show is that if now these were quantum observables that you're measuring, A1 and B1 are some quantum observables. If they are spin half particles, you can take a measurement of spin along some particular direction. I said A1 and A2 are two possible experiments. They can be measurement of spin along two different directions, A1 and A2. And similarly, B1 and B2. Okay? And then you can see that this quantity is not bounded by 2. You find this average, you do the expectation value like they teach us in quantum mechanics courses, and you find this value can exceed 2. It cannot be larger than twice root 2. How much is twice root 2? Approximately? Huh? 2 point? Hey, help me. 1.4, right? 2.8. So it can be quite large compared to 2. Now, you see, when we are doing this very simple arithmetic here, there are many assumptions which we are making. And those assumptions are precisely what Einstein assumed, things like realism. For example, when we say that, if Alice was measuring A1 and Bob was measuring B1 and the outcome was A1, B1, and we are multiplying them, that is, we are assuming that there is some value for that observable which existed, and then we are multiplying it. Because when we are multiplying A1, B2, it's a different experiment. It's a different instance. And then you are combining all of them together. So when this does not make sense actually, unless you assume that these properties of A1 and B1 had definite values before you were making these measurements. If you're making measurement along spin direction, let's say Z, and you get some value, you're assuming that that value existed as a property before and after you have made the measurement. So that you can assign these values, and this whole thing makes sense. So that is realism. So it looks like a very simple arithmetic, but behind that you have this deep sort of philosophical sense of this. Locality is also important in the sense that we are assuming that there is no strange correlations like what might have existed at that time or some other, but it's slightly more subtler to see that. So this is called CSH because of these authors, Clauser, Horn, Shimoni, and Holt. You can't again read these names on this, but they wrote this paper in 1969, and they derived this kind of inequality. They pointed out that you can have quantum violations of this obvious inequality, which is now we'll call this classical, if it's less than or equal to 2, and this as quantum. So under the assumptions of Einstein, Podolsky, and Rosen, this cannot exceed this cannot exceed 2. And therefore they said, let's do an experiment and let us see whether this is being violated or not. And Clauser was the experimentalist who took this forward in a very big manner. And there were these fine atomic physics experiments where they were measuring the photon polarization, which is like spin. It can have two different polarization directions if you measure them along any particular direction. In fact, Clauser was part of the Nobel Prizes in 2022. Yeah, I think you're right. I think both directions are going in one direction. Let's see. Yeah. Okay, there is irreversibility here. Yeah. I can finish the talk very quickly. Okay, can you probably... I think you're oscillating. No. Good. Just John Bell, yeah. Thanks. Yeah, so John Bell, there is a John Bell Day, which is coming up November 4th. So we are fairly close to that. It's nice, thanks. He couldn't get the Nobel Prize because I believe they don't give Nobel Prizes posthumous. But otherwise, he is the one who set the whole thing. As I said, the CHSH inequality is rather simple to state, but actually Bell's work was the deep one, where and then there's Bell inequalities, where he showed that it will be violated if there is no if there's locality and realism kind of assumptions, classical assumptions were not there. And for the students, I would like to say that John Bell was a particle physicist from CERN who claimed that he was doing quantum mechanics on Sundays. Okay, so it was kind of hobby for him. And also, I think what is interesting, and I think we should take away from this, is that he challenged major authority like John von Neumann. There's a von Neumann's theorem, which he called absurd. And so don't believe things just because somebody has some authority on it, question it, and see for yourself, I guess. We should all be doing that. So that is in honor of John Bell. But the people who got the prize were Clauser and Aspect and Zeilinger. And you can see these proposed experiment to test local hidden variable theories. These local hidden variable theories are those assumptions which this entire set of locality realism assumptions were put under this heading of local hidden variables, which meant that statistical mechanics, the uncertainty in quantum mechanics which we see, they perceived was not because of something fundamental, but because there were some degrees of freedom which we were not getting access to. There was some underlying hidden variables that we were not getting access to. And therefore, when we are seeing this random, it's like statistical mechanics. We don't believe that statistical mechanics is statistical because Newton's laws are statistical, but because too many particles are there, we're not going to observe all of them. We make an ensemble out of it. So that is the kind of thing which they showed was not true. So there is a series of experiments over 3 decades actually. So like let's look at some of this early 1978. So there is a source of this entangled head plus tail kind of particles. In all of these experiments, they are really photons and they are polarization entangled. And then there is this event-ready detectors. There's coincidence circuit. You should know that the photons which you're detecting, Alice and Bob detects, are the entangled pair. It should be from the same entangled pair, not from some other entangled pair. One from one pair and the other from the other. So you need this coincidence circuit. And then there is Alice and Bob have these 2 analyzers, so they can set it. So Bob sets 2 possible directions, and Alice 2 other possible directions, and they measure whether the spin is up or down. There is a neither counter, so that is a dark count. They are not, for some reason, you've lost the photon. Okay, and then they do this measurement, and then they do a lot of measurements. Then they find the CSHH quantity, and they see whether that is being violated. The inequality is being violated. So there were several developments. So Aspect experimental realization of EPR, a new violation of Bell's inequality. Agreement with quantum mechanical predictions led to the greatest violation of the generalized Bell's inequality ever attained. Experimental tests using time-varying analyzers. So the sources of entangled photons started getting better. And there is a very nice article which I will point out, Physics Today from 1985 by David Mermin, with a provocative title, Is the Moon There When Nobody Looks? Reality and the Quantum Theory. Einstein maintained that quantum metaphysics entails spooky actions at a distance, like that steering which I talked about. Experiments have now shown that what bothered Einstein is not a debatable point, but the observed behavior of the real world. That is, there is that kind of steering which is possible because you're violating the CSHS inequality. And this particular title about the moon is what I said about the property of objects, whether the property is there before you have measured it or not. Is it manufactured by your experiment in some way? And that is the realism part of it. So it seemed to violate these kind of realism. So here is a more recent experiments of Zeilinger, violation of Bell inequality, strict Einstein locality conditions. Because this locality, I said that they have to be separated by space-time separation, so that there is really no argument that there is some force which is influencing this correlation, producing these strange correlations. This was the first one which achieved that. To achieve this condition, the observers Alice and Bob were spatially separated by 400 meters across the Innsbruck University Science Campus, which in turn means that the individual measurements as defined above had to be shorter than 1.3 microseconds, the time for direct communication at the speed of light. So there were these two, so your 400 meter, you had some photons which were traveling in some fiber optic cables, presumably. And then a much more recent experiment, you can see 2015, is a very interesting one where this is experimental loophole-free violation Bell inequality using entangled electron spins separated by 1.3 kilometers. So this was very difficult to think about. Photons were easier to, because they would not interact with other photons themselves, and therefore they could retain their entanglement over large distances, whereas electrons, it's very difficult for them to remain entangled over large separations. So a very ingenious experiment here where they are using photon entanglement to swap to electron entanglement. So they are transferring entanglement from photons to electrons, which were separated by 1.3 kilometers. And then they see that the violation here, let me read out, 2.42. So we said that 2.8, 2.42 plus or minus 0.2. So clearly above 2. And so this was the most recent experiment which showed that indeed there is this correlations over long distances. So maybe I can stop to ask if there is some immediate question or comment, because we are transiting into something else. Yes, please. Each instant, they have one pair and they are measuring it. No, so they are measuring either A1 or Alice will measure either A1 or A2. They can't measure both. They are two different experiments. So they can measure like Z or X. She will choose which one she chooses. No. Over many entangled pairs. So you have a million photon. There's a source which is producing for you these entangled pairs. They're all identical. State is identical of what comes out, like head plus tail. Huh? Exactly. So it's the same state as far as quantum mechanics is concerned. But different particles, because once you make a measurement, as you know, the state will be destroyed. The state of the particle will be collapsed into one of them. Exactly. So that is, I can't go back, but A1, B1 simply means that Alice has measured A1, Bob has measured B1. There are two measurements on two particles which are entangled. So there is a copy of, I mean, there's no copy. There are these two particles which are entangled. Bob is measuring B1, Alice is measuring A1 on each of their particles. And they get, let's say, +1 and -1. They multiply that. That is A1, B1. That's the meaning of A1, B1. Now, in another entangled pair, let's say that they measure A2, B2. Again, they will do the same thing. They will do a product. This is what I said, that there is the assumption of realism behind this. When you are adding all of them together, you're actually adding different experiments, but on the same state. Yes, yes, exactly. Yes. Who will take the product? Because at the end of the day, at the end of the experiment, right, a million particles are there, they will do these measurements, they will get together. Because in order to find correlations, you need to get both the data together. So they have to meet or they have to send it to some neutral referee to do the analysis. They have to, yeah. Because in fact, that is one of the, it's a good question. They have to get together. Look, I mean, I said that Alice can steer Bob's. So it looks like there is action at a distance, right? Instantly the state has changed. Alice knows, or even this thing about knowing, Alice knows what is the state of Bob without any information coming from Bob. But it doesn't violate any, it's not information which has traveled a distance, because she cannot, for her to inform Bob that this is the state of the particle, you measure this and find out, that requires communication at the speed which is less than light. Bob, the ignorance of Bob remains the same before and after the Alice's measurement. Alice may be wiser, but Bob's state is just as random as before. Unless Alice makes a phone call to him and says, if you make this measurement, then for sure you will get +1. He can disbelieve her, but now this is not happening at a speed which is greater than light. So that's why relativity is compatible with entanglement, and the quote unquote spooky action at a distance is after all not that spooky. Yeah? Yeah.
Just to clarify last question.
Hmm.
In your screen, there was a sum and then there is an expectation.
Yes.
You are going to split it into expectations now, right? So that you can compute that sum. That's what my guess is.
Yeah. Yeah. You're going to take the sum and then do an expectation value. Then they take a modulus. It's less than or equal to 2. A modulus is less than or equal to 2. And quantum mechanically, you're going to take expectation values in a particular state, which is this entangled state of these observables. Classically. Classically. No. The total can be only 2 or -2. There are 4 terms, one with a minus sign. So that total thing, A1 into B1 minus B2 plus A2 into B1 plus B2. This entire thing can be either +2 or -2. That's all. Now you're adding many +2s and -2s as you're averaging it. So it cannot be anything larger than 2 or anything smaller than -2. So the modulus is less than 2. Yeah. Quantum mechanically, it tells you that you cannot assign, just eigenvalues are still only +or -1. Nothing strange about it. But you can't just add eigenvalues of incompatible observables and make some sense out of it. If you take x plus momentum plus position, momentum has eigenvalues, position, this eigenvalue of x plus p is not the eigenvalue of x plus the eigenvalue of p. They don't commute. That's the point. Anything else? These are subtle matters. I think we have to keep thinking about them. But also quite simple at some level. It doesn't involve a lot of mathematics. Okay, so let's proceed. Okay, I just put here the fact that, things have gotten simpler to produce entangled photons. You can do some nice nonlinear optics and get some crystals, I believe, to make, to do some down conversion, and you can create entangled pairs of photons, polarization entangled photons, although not very efficiently, about 1 in 10 power 5 or so pairs of photons will get entangled. And this is a big research topic, is to create better sources of entangled photons for use in various communication tasks and so on. So in fact, the shared randomness, which I talked about, can be used in cryptography. So in 1991, Alice and Bob want to share some key, secret key. Then they can do this. They share these entangled things and then they make measurements. They can share, because of the shared randomness, they can share some very random strings of zeros and ones and that. So, and this is quite, the attack by an eavesdropper, Eve, can be easily detected because the quantum mechanical state will be disrupted by a measurement, unlike classical. Classical, you can measure the state of a particle and the state need not change, but quantum, it will change. So this leads to security. So this was the practical aspect of that same thing. So now, I'm just putting on this slide some basic things about any two-level system like this polarization states of photons or a spin of electrons is a two-level system, or a two-level atom is just called qubits because of it has these two levels, 0 and 1, and any superposition of that is the state of a qubit. So a qubit is just a simple two-level system which can have coherent superpositions, okay? And you can produce these things, Ising interaction, like for example, I've just given an example. You can take an Ising interaction between two spins, ZZ interaction, and if you have the two spins in the state 0, let's say that's the state down spin, then nothing happens because sigma z is an eigenstate of, the down spin is an eigenstate of sigma z. However, if your initial state was, or if your interaction was XX instead of Z, it's not an eigenstate and it will produce a maximally entangled state. So entangled states are not that hard to make. In fact, they've always been there and they are the core of chemistry, as Professor Sebastian here would tell us. So any natural interaction can create entanglement, and even they can create maximum entanglement. There are measures of entanglement and so on. Okay, so here is an example of that. Okay, so using entanglement. So as I said, we are now in the 1990s. There was this classic paper by Bennett et al. Called Teleporting an Unknown Quantum State via Dual Classical, and it's a long title, but this, you can say, dual classical Einstein-Podolsky-Rosen channel is just precisely those states that I've been talking about, HH plus TT, maximally entangled states. So I'm not going to go into the details of this, but let me just tell you what this cartoon kind of tries to convey about teleportation. Imagine again, Alice and Bob, these are our players, and they share this entangled state, head plus tail, this magical state which has these correlations which are beyond the classical. And what can they do with it? It turns out, quite interestingly, that let's say that Alice has another qubit with her. There's a two-level system with her, and she doesn't even know what state that is. She doesn't know what state. She wants to do something and convey to Bob. She can't send that particle to Bob. All she can do is make a small phone call to Bob in which she conveys 2 bits of information. Just 2 bits. That means she can say 0011, 10, or 11. That's it. She has to now convey this to Bob, and Bob will do something at his end to his particle, and the state, the final state of Bob's particle will be the state of the unknown particle with Alice. So Alice will then be said to have teleported that unknown state to Bob using just 2 bits of information. Just think about it. If I was to give you that qubit state, it's alpha 0 plus beta 1. Even if I know what alpha and beta are, to convey to you, I need to tell you what is alpha and beta. 2 complex numbers, which means how many bits of information I have to give you. In principle, infinite, because each of those real numbers, I need to give you a very large number of bits for any precision, right? But Alice does not even know alpha beta. She doesn't know what that state is. But at the end of the day, Bob has exactly alpha 0 plus beta 1. So this is the magic of teleportation, which is possible because of they are sharing an entangled pair. So in fact, this entanglement is a resource for this kind of quantum teleportation, which is a unique quantum protocol. I'm not going to go into the details of that, but the mathematics is rather simple. And I think a course in quantum mechanics should be sufficient to understand that. And if you haven't come across it, please look at it, and it is really mind-boggling at some level. And practical implementations have been claimed of teleportation. So again, this is like satellite to ground teleportation has been claimed to have been achieved. Ground to satellite teleportation, so very long distances. And of course, quantum computing, we are now in the era of quantum computers. So a collection of qubits you can put together, and they are all interacting, but you can try to do something which is not possible to do with just bits, the classical computers. And there were 2 algorithms in the mid 1990s called the Shor factoring algorithm and Grover search algorithm, which became really the motivation for much of the development of the technologies which we are seeing today. Shor's factoring algorithm made factoring large numbers easy on a quantum computer. Easy meaning polynomial in the number of qubits. So, but factoring numbers is central to most of all our cryptography, all our security, our credit card, our bank, everything relies on something called the RSA protocol, which relies on the difficulty of factoring a big number. You can multiply 2 numbers, but factoring numbers is a well-known, although not proven to be hard, but believed to be a hard classical problem. And therefore, if you can find an algorithm which will do it in a very short time, this created a lot of interest. And its core, at the core, there are 2 things. One is the Fourier transform, and it does the Fourier transform efficiently. The Shor algorithm uses Fourier transforms, and the other thing is called modular multiplication. So it takes these 2 things and it then creates it. Grover's search algorithm searches earlier we used to have these phone books, now we don't, in which if you have the names of people, you will find the numbers. But the names of people will be ordered alphabetically. So it's easy to search if you know some person's name, but if you know the phone number and you don't know the person's name, obviously it's hard, because it's not ordered according to phone numbers. And therefore, that's an unstructured database search. And in which case, if there are n entries, you can only find that with n trials. What Grover showed was that if you had a quantum computer with this kind of entangled qubits, it's possible for you to do it in square root of n. So it's not exponential as in the Shor algorithm case, but it's still a very important thing. And now there is this NISC is it refers to this particular noisy intermediate quantum computing era where there is one acknowledges that it's difficult to get an exact noise-free environment, but still one can probably do a lot. That's what is being tried, and there is an amazing number of developments. And not this is from IBM, which relies on a superconducting technology, but there is a whole lot of work around other, especially cold atoms. Rydberg atoms and so on, which are very promising as arrays of qubits which can be entangled with each other and can create complex states in which to do these kind of computations. Okay, so okay, maybe I will skip this. This tells especially students that we can actually, you can play around with things like a Qiskit, which is like an IBM program, which is based on Python, to create many of these states and to do actual experiments, which are like this Bell test and so on. It's possible to do it with simple circuits. And simulation of complex quantum systems. So now I'm going beyond 2 qubits or a few qubits. There is a collection of qubits in a quantum computer such as this. And there is a race to what is called quantum supremacy, to say that we have done something which is impossible on a classical computer. And all that is relying on, so this kind of a figure you should read as this is time. And each of these squares is a single qubit, operation on a single qubit. And these are the gates which are operating on that. And these are 2 qubit gates which are connecting these two, interacting these qubits here. And there are these experiments which involve about 50 qubits in which you put in a very simple state, and then you get a highly entangled state of many qubits. And then you make measurements on that, and you look at the measurement outcomes, and you see what is the sampling of that measurement outcome from. Like these kind of experiments involve about 50 qubits. 50 qubits is like 2 power 50 dimensional space, which you can't do on a classical computer to find out what is the outcome samples. So, but you can do this on a quantum computer and see that what those samplings are. And so that's the claim to these kind of supremacy experiments. And then there are these studies to construct what are called maximal entangled states. What states are more than just these kind of head plus tail. If you have many coins, many qubits, what are the maximally entangled states you can create out of that? There are applications to what are called error correcting codes, secret sharing, dense coding, etc. I've already said something about quantum key distribution, quantum random number generator. This is again something which people worry about a lot, creating genuine random numbers. And quantum mechanics seems to give us a pure source of uncorrelated random numbers. And so there is this race to develop genuine random number generators, and there are claims to even now phones like Samsung Galaxy phone quantum, where they claim that their random number generator is a quantum random number generator. Okay, so I think I'm now at 3:30, so I need to make a choice. Hare Krishna, yeah. The Euler problem. How much is the, yeah, okay. Let me see if I can say that, but maybe even just this 3 qubits. If we go beyond 2 qubits, let's see, life gets actually very interesting. And this is where we are stepping out of even the, the 1960s kind of thing. This is called a GHZ state. You have three particles which are 0, three particles that are 1, which are superposed. You can think about it as up, 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 plus down, down, down. Okay, a state like this. This is called, so this state is a three-particle state, which is such that if you ask what is the entanglement between any two of them, any two possible qubits, it turns out that they are not entangled. But all three are entangled together. Okay. To see that, you'll have to see what is the reduced state of two qubits, and they will be some mixed state like this, which can be written as a superposition of states themselves, and therefore this is what is called a separable density matrix. Okay. So what I want you to get away with is the message is that this 3-qubit state is maximally entangled in some sense with each other, but if you just take any two of them, they are not entangled with each other. So this is again something which we can't really, well, we can visualize it. So some people have visualized it. Maybe I will skip this part. Oh, oops. Ah, okay. You did some magic. Something happened. Okay, so we can visualize this by means of a Borromean configuration, which is appears in nuclear physics and other areas of physics. It's like three rings, which no two of them are linked to each other, but all three of them are linked together. So if you see this picture here, if you concentrate on two rings, let's say this one and this one, you can see that this ring is completely above that ring. It's not connected. And similarly, this ring and this ring is above that ring. So all three of them are actually unconnected, but together they are connected. And you can see this in a lot of places. And this one was near my home in a temple in Tiruvanmiyur, so called Marundiswarar. This is three triangles in exactly this. So these are Borromean triangles. And so this is like that entanglement in the sense that no two are linked to each other, but all three are linked together. So no two rings are together, but all three are there together. In fact, the logo of the Institute of Mathematical Sciences in Chennai is very similar to that of the International Mathematical Union, which also has this three things together. And I encourage those of you who haven't done this, or even those who have done it, because I keep forgetting how to do it, to actually do it. So before coming here, I had some other better things, but I forgot back home. So I had these cables which I tried to put in that configuration. You should try it. Okay. That is okay. Now it's come out. So, okay, bad. So, but this is what you want to do. There are these three, 1, 3, 1, 2, 3, right? And you want to put them together such that, like this one and this one are not linked. They're not, clearly they're not linked. But now you have to put them all together such that all three of, now if I start doing it, it'll be the end of the talk. But you can try it, and afterwards, if you want, you can come and do it. It's quite simple. But anyway, so this is the kind of things which will happen if you go beyond two particles. Multipartite entanglement is a topic of research today. You can take more. You will get more. So in fact, I had a thing which I bought from Munnar. It's not only temples. Everywhere you can find it. In Munnar, I found a stand, 5 of them. They had made a beautiful stand. You can put things on it. And that had 5 such things which you can put. Okay. So, but those are like GHZ states with 5 spins up plus 5 spins down. Any number can be done. Okay, so those are all called Borromean, those are all called Brownian links in knot theory, I believe. Okay, so now let me talk about this problem of Euler, which we did. Again, maybe I will need at least 5 minutes. Is that okay? If you have the instinct for that. So our problem was the following. Here we have something like head plus tail, which we said was very useful in all this CHSH inequality and all that. This is the GHZ state, which also people consider as maximally entangled, like this Brownian. Okay, what happens more? Let's take this 0, 0, all zeros plus all 1. It turns out, and it's very easy to see that this is not maximally entangled in any way. Okay, so in fact, more than 4 qubits, more than 3 qubits is difficult to create what are called maximally entangled states, and it depends upon your choice of what is the measure that you are looking at. There is one class of states which people have studied, which says that let's look at, if you have n particles, each of dimension d, we can even go beyond qubits. We can go to why only 2 levels atoms. You have atoms of any number of levels. So 3 levels, 4 levels, and so on. So you have n particles, each of d levels each, and you can ask, you can take half of them and say, can this be maximally entangled with the other half? And you can take any half of them and they should be maximally entangled with the other half. Is this possible? So this was the question of, this is the definition of what is called absolutely maximally entangled states. And it was known that there are no absolutely maximally entangled states of 4 qubits. But it was also known that there are absolutely maximally entangled states of 4 qubits, that is 3-level systems. So maybe I will actually transit to that, but there is something about the uses of these maximally entangled states for a generalization of teleportation called parallel teleportation and so on. So there's a lot of use of that. But let me get to this particular aspect of 4 particles. 4 particles, qubits, it was known that you can't have this kind of states in which any 2 is maximally entangled with the other 2. And for 4 particles with 3 levels each, it was known to be possible. In fact, it was known to be possible for every other thing except qubits and a 6-level system. Interestingly, 6-level systems, it was not known whether it exists or not. And the fact that it was known for every other thing comes from a very interesting construction, which is known as an orthogonal Latin square. So maybe this is something which we can now forget about quantum mechanics and go to something like a Sudoku puzzle. So let us look at this configuration, 2 by 2 square, in which you are having an ace and a king, and we have filled it such that there is only one ace in a row, one king in a row, and similarly in a column. Okay? And let's take another 2 by 2 array in which you have a spade and a diamond, and you have one spade and one diamond in each of these. Now let's put them together, these things. So each of this cell, the first cell is ace, and I think I have something here. Yeah. So, okay. So let's say that in the first cell we have ace and diamond. The next one, it should be different in both the type of card and the type of, what do you call this? Suit. Okay. So this can be king and the other should be spade. Now, is it possible for you to, what can come here? Ace should become king and diamond should become spade. But that is the same as this, right? That is the same as this. So it does not have ace of spade and king of diamonds. So you say that these two are, you can't put them together, any 2 by 2 Latin squares. So these are called Latin squares when they don't repeat along any row or column. You can't put 2 of them and get all 4 possible outcomes out of it. Whereas for 3 by 3 arrays, it's possible to do that. here is this array where you can see that there are three possibilities: ace, king, and queen, diamonds, clover, and spade, and they don't repeat along any of these columns or rows, and all 9 possibilities are there. There are 9 possibilities of king with clover, king with spade, king with a diamond, and similarly with queen with all 3. There are 9 possibilities. All 9 possibilities exist, and this is called an orthogonal Latin square. These 2 Latin squares are called orthogonal, and this is an orthogonal Latin square. And Euler here in the 1700s, he uh, he postulated that there is clearly no orthogonal Latin square of size 2. Size 3 there is, and then size 4 and 5 he constructed. 5 is rather easy, 4 is harder. And then came the problem of 6. And a very curious question, which has exercised for some time the ingenuity of many people, has involved me in the following studies, which seem to open a new field of analysis, in particular study of combinations. Question revolves around arranging 36 officers to be drawn from 6 different regiments so that they are arranged in a square, so that in each line, both horizontal and vertical, there are 6 officers of different ranks and different regiments. So there are 36 officers, 6 regiments, 6 ranks, and they should be arranged in the 6 by 6 array such that there is no repetition of a rank or a regiment. I believe that when there are these 36 officers and the Tsar comes to inspect them, he will randomly pick a row or column and walk along that. He should sample each regiment and each rank unbiasedly. In fact, this entire field was developed by the School of Indian Mathematics and the ISI, Kolkata, from precisely agricultural point of view. How do you do how do you sample? Suppose you had some fertilizers, different seeds and fertilizers. How do you test it out? So, in fact, some remarkable work was done by them. But Euler kind of conjectured that for 6 it does not exist, and he went on to conjecture that it exists for all odd. He proved that, and he also proved that it exists for all multiples of 4. So the only thing that remained was divide by 4 and you get remainder of 2. 2 plus 4n. 2 clearly doesn't exist. 6, he thought it doesn't exist after trying for a long time. Then he conjectured that it doesn't exist along all of this. So this conjecture remained for a very long time. In 1900, Terry showed that in fact 6, it does not exist. And then in 1959, there were these so-called Euler spoilers, R.C. Bose and Shrikande. Bose was earlier in ISI, but when they did this work, he was in the US. Shrikande was a student. They showed indeed that it exists for all possible square sizes except 2 and 6. So 6 still remained untouched. And why does this help us with our problem of entanglement? Let's take this particular orthogonal Latin square. We have put, instead of kings and so on, just numbers. So we have a 3 by 3 array in which no number is repeating along the first row. First number is not repeating. Second number is also not repeating along any row or column. Okay. Now let's take this and create a quantum state out of this in this following way. So we take the address of the cell, which is 0, 0, and the input into the cell, which is 0, 0. So this will be the state of these 4 particles, okay, of a state of, these particles have 3 levels, 0, 1, and 2. And the next one is this address of the cell. This is the 0th row, first column. So 0th row, first column, entry 1, 1. So this is the next. And so you will get these 9. You see, this is the second 2, 2, second row, second column. This is 0, 1, 2, and the entry is 1, 0. So the claim is that this kind of a state which we have constructed from this has precisely this property that it's maximally entangled across every cut possible. So it's in that sense maximally entangled, highly entangled state. And because there exists orthogonal Latin squares in every square dimension except 2 and 6, people knew that for 2 it did not exist by other proof, but for 6 it was not known. So this was the smallest known unknown case. And to cut a long story short, we kind of showed that they exist, these states exist, but let me not go into the method of this. But let me say that there is a quantum orthogonal Latin square in a way which exists. So we displayed that exactly by all this, by writing a 36 by 36 unitary matrix. Interestingly, the entries of this matrix are very simple. They consist of the golden mean, mysterious, we don't know exactly why they appear, but it contains the golden mean and the 20th roots of unity. Okay, we would like to understand this further, but at the moment it's just a construction that works. Okay, let me, so here is the result written in terms of something like this. So there are again entanglement within each cell. You can't have just ace and clover and so on, but you should have superpositions of these, which is creating entanglement. Okay, so now in some sense, these cards, the entanglement is there between the suit and the type of card. Okay, so each of these things have this nice entanglement structure, and we kind of illustrated it with, instead of coins, now it's a 6-level system, so these are like dice. You have 6 possible outcomes, and these are 4 dice. If they are entangled in this way that we have, if you toss these 4 coins randomly and you observe 2 of them, any 2 of them, it determines the state of the other 2. You know what is the state of the other 2. So this is the kind of entanglement properties which arise out of this. Yeah, so there is a lot of popular write-ups about this. The people involved in this, I should acknowledge the most important person was my last PhD student, Suhail Ahmad Radha, and then Adam Burkhardt and the group of Karol Szyszkowski in Poland, Jagiellonian University, Wojtek Bruzda and Grzegorz. So these guys were all very crucially involved in this work, and they kind of showed that this classically impossible problem of 36 officers, you can lift it into the quantum and then solve it. There are popular write-ups for those who are interested. There is a write-up in Quanta, Euler's 213-year-old impossible puzzle gets a quantum solution. And for those who want a more technical thing, there is a nice notebook in the Wolfram community written by Suhail on the problem of 36 officers. You can play around with the matrices and see the state. So let me finish. Entanglement is a fascinating aspect of quantum physics with deep and wide applications and implications. Many unsolved problems and puzzles. Especially about multipartite entanglement. I did not mention its uses in condensed matter physics, Hall effect, a whole lot of different correlated electron systems, but that's being really intensively studied. Okay. Somehow it's not going beyond that. Is there anything beyond that? Yeah. Okay, yeah, that's fine. Just leave it as that. That's fine. So one thing which I did not talk about, because it's not that, I can't go into the technicality of this, is the separability problem. I talked about entanglement in pure states mostly, but if you look at mixed states, There's a lot of open problems, even two Q trits. One does not know how to say whether something is separable or not, how to measure that very well. There are some interesting problems of what are called mutually unbiased basis, bound entanglement. You can look, there are many sources of open problems. This is one article, 5 open problems in quantum information theory, which appeared in 2022, PRX. Some of these might be solved now. And there is also an open list of problems maintained by the Institute of Quantum Optics and Information in Vienna. So it's an exciting time for us to understand this better. And in fact, it's as we saw, its beginnings, its origins go back to right from the founding figures of quantum mechanics. So thank you very much for your attention.
So thank you very much, Professor Arul, for a wonderful lecture. I think we can take a few questions and then.
Hello. Sir, for two entangled photons, let's say their polarization states are entangled, can at the same time, can any other degree of freedom, like a momentum, can be entangled?
Good question. Yes, they can be. So sometimes people call it hyper entanglement. Yeah, it's possible. There can be many degrees of freedom. It's some way like this going into many particles. You know, you have many properties which are getting entangled. Yeah. So I mean, the spin is or polarization is one degree of freedom. You can have other.
While talking about CH inequality violation, you talked about some loopholes. What are those loopholes?
One is this locality loophole, which they talk about, that in fact they have a space-like separation. So you have to ensure that that is there. And then there are these dark counts. You know, you might be on one side you might have a dark count. You don't see the photon, and the other side one may see a photon. So there are these kind of so there must be this coincidence must be very good. There's a bunch of those kind of issues.
So just about that 36 square tiles.
Yeah.
So from what I understood, so you have 6 symbols and you have to put those 6 symbols together. 2 sets of 6 symbols.
Yeah,
so there
exactly.
will be 12 sets of symbols.
Exactly.
Symbols. But
Exactly.
in the figure that you last showed, I could see more than 12 sets of symbols.
Yeah. Yeah.
I was expecting like 12 symbols altogether of different color. 6 from one set and 6 from the other set.
No, you will have 6. They don't bother about the color. The color is only for you to distinguish. So there is ace, there is king, there is 10. I guess it's starting from maybe 9 even, right? 9, 10. Then there is a jack. Then there is king, queen, and ace. That's 6 for you. Forget about the colors. The colors are only for distinguishing. And similarly, the other one. There are this one, clover, spade, diamond. Then this one, this flower, and this star, that's 5. Heart. There'll be 6 of them. There are only 6. So each one of them is a 6-level thing. Yeah. Yeah, thanks. I had to rush through that.
This kind of thing, does it give any insight into what quantum entanglement is?
Which kind of thing?
This kind of analysis.
I think so. I think what we are trying to do here is to understand the nature of entanglement in a multipartite sense. For example, even that Borromean which I showed you with those 3 particles, the fact that you can have 3 particles which are entangled with each other but not amongst each other is a type of thing which you will obviously it doesn't make sense with 2 particles. When you go to 3, there is something called a tripartite entanglement, which is something which is shared between all 3. So, and there are 2 types of states: those in which you have this, and those in which you don't. That it vanishes. When you go to more than 3, it's much more murkier. What are the various types of entanglement which are present in this? You can ask, suppose you have 6 particles, suppose you have, like in this case, we have only 4 particles. Even 4 particles is interesting. You can ask about the entanglement of 1 with the other 3, 2 with 2, and all 4 taken together. So in fact, this is missing. All 4 taken together, what may be called a 4-tangle measure. There are suggestions for qubits as to what they may be, but in general, it's missing. So this particular study, which has to do with absolutely maximally entangled state, one has defined what is absolutely maximally entangled, but whether in some way it is practical for, let's say, some information task, teleportation or something like that, that will determine what kind of entanglement you want. So I would say that yes, this kind of analysis certainly, like for instance, the fact that there exists no classical problem tells you something about the nature of the entanglement. Yeah.
Can you mention some of the applications of quantum entanglement in quantum gravity?
I'm
How
no
it finds
expert, but
application?
yes. So there is a lot of that, a lot of connections between. So, in a way, quantum gravity is basically a study of black holes, quantum black holes. So you can think about that kind of thing. And there is the so-called ADS-CFT correspondence, which is connecting a field theory to gravity problem. And so, yes, so there are these, there is a study of, so entanglement plays an important role, let's say, in the study of quantum gravity. So I can't specify anything very much more, but for instance, even the very famous, paradox, so to speak, of you have two qubits. One is going into the black hole, and the other is outside. What happens to the entanglement? The information paradox and things like that. They're all part of one set of things. So I would say that entanglement is being used as a property to understand quantum gravity.
So any other questions?
Thank you, sir, for the talk. My question is regarding the experimental verification of this Bell's inequality or violation of it. So how do you make sure that the pairs are actually entangled or not? Like, for example, you create 2 electrons that are entangled. you separate it to 2 kilometers away, and you do a coincidence measurement also. And that measurement has to be coincident, and you can take the speed of light as a limit before which you have to make the measurement. But how long does this electron stay in an entangled state, or it's just infinite?
Actually, as I said, yeah. So there's a last experiment which had electrons, but that involved some swapping of entanglement between electrons and photons. But if I just take your question as how do you know that two particles are entangled before you start doing any CSHS kind of measurement, the answer would be you have to do a what is called a tomography of that set of particles. Suppose somebody gives you a source and says that here these photons which are coming out of it are polarization entangled. You can do a joint measurement on these things. So suppose you have these two photons, you can do a joint measurement and figure out what that state is. It's not Alice and Bob situation. Alice and Bob situation, they are separated. They're not making joint measurements. But you don't have to tie your hands up like that. If you just want to, what is called benchmark the states which are being produced. You can make joint measurements, the Bell state measurements are possible. And you can do what is called tomography, which is basically figuring out what the state is. And then you can do the separated measurements and so on. Once you're confident that indeed what you have is an entangled Bell state or something, like head plus tail, then you go ahead and do it. So that's for something you need to do first.
Any other questions?
Thank you, Professor Arul, for a wonderful presentation. Now, on behalf of Professor Valsakumar sir's family, Mrs. Leela Valsakumar would like to present a memento to Professor Arul. Please, sir.
It's a lot. Thank you. Thank you for calling. That's a gift. Calling me is a gift. Thank you. Thanks. I hope it is fun. Oh, wow. Oh.
It's an Aranmula mirror, sir.
Oh, okay.
It's a
I've heard about
heritage,
it.
UNESCO